The next presentation. Okay. Hello, Catalin.
Hello. Are
So
you
the next.
well?
I'm here. It's a pity that you are not with us. So the next presentation will be done by our colleagues from Polytechnic University of Timișoara. The topic is from artificial intelligence to deep learning, and the presenters will be Professor Catalin Caleanu and Associate Professor Georgiana Simion. They are both with the University of Polytechnic University Timișoara, with the Faculty of Electronics, Telecommunication, and Information Technologies, and they are working in deep neural networks, virus cards, systems, embedded systems, machine learning, and computer vision in the applied electronics department. So, Catalin, the floor is yours.
Thank you very much. I hope that you are able to see my screen well.
Yes.
Could you confirm me? Okay, thanks. And once again, thanks for the invitation. It's an honor for me to be here today with you. Unfortunately, my colleague Georgiana is not able to join the meeting today, so I will make the whole presentation with the following topics. First of all, I will try to define some elementary notions like artificial intelligence, machine learning, deep neural networks, and deep learning. In this sense, there is some kind of overlapping with what have you seen already, especially with Daniel's material. But most of the presentation is more like a tutorial focused on what kind of tools, both software and hardware, you are need in order to implement such kind of applications. So this will be the last part of the this topic will concern the last part of the presentation. Now, first of all, I would like to establish a relation between these concepts, starting with the more general one, artificial intelligence, and finally deep learning. And you see, basically each concept is essentially a component of the previous term. Basically, as we will see immediately, machine learning, it's a subset of artificial intelligence concerning, and is concerned obviously with the learning aspect and so on. So please keep in mind this representation, and let's point out in the following the particularities of these paradigms. And I will start with, as I said earlier, the most general term, artificial intelligence. It was coined many years ago, 1955, as far as I remember. It was John McCarthy from Stanford which introduced this concept. And the reason for its appearance is pretty obvious. We would like to introduce some, let's say, features of human intelligence into artificial systems, into artificial machines. What exactly I'm referring to? For example, the ability to learn. Let me see if I'm able to use a pointer right now. Yes. So it will be nice to have a machine which will probably autonomously learn, be able to learn or to reason in a similar matter, in a similar way with humans, to be creative eventually. And I may say that due to these very bold goals, AI, it's a heavily, intensively researched field of science nowadays. Since now all these applications, implementations lie in the so-called artificial narrow intelligence. What does it mean? It means that such systems are able to solve some particular tasks in opposition with this general intelligence, which is somehow on par with human capabilities. And of course, perhaps in near future or not so distant future, we will see also artificial super intelligence. These aspects are maybe more philosophically oriented. Why? Because it's hard to define the concept of artificial intelligence, and more exactly when and to which degree an artificial system comply with these concepts. Probably today we are around this general intelligence level with some of artificial intelligence systems. The domain is also very intensively researched and important due to the applications which could benefit from it, starting with, I don't know, virtually every domain has or could benefit of such applications. Healthcare, think about computer assisted diagnosis, for example. Automotive, think about autonomous driving. Economy, finance. There are a lot of economic indexes, exchange rates, stock prices, etc., which could be pretty good predicted, approximated by machine learning models. Even agriculture could benefit from such technologies. And think about drone surveillance and smart agriculture and concepts like that. So yes, this interest is fully justified because once again there are many applications. Now descending down in this hierarchy, I would like to say some things about machine learning, which is, as you could see from this block diagram, the part from artificial intelligence concerned with mostly with the learning aspect. Okay. Along with other paradigms like I don't know, expert systems. See, we are in the we are interested right now in deep learning, in how to link artificial intelligence concept to deep learning. So I will choose from now on to present you more about the so-called connectionist approach in opposition with what we are having in the rest of the paradigms, which are probably symbolic approaches. We will go in the following, in this area, by telling you that we could broadly classify this learning into supervised learning, and probably this is the most common type of learning involved in artificial intelligence. What does it mean? Well, pure and simple, there is a supervisor. Okay, what this supervisor knows is how to associate a certain input with a specific output. Okay, so yes, in this case, we need a data set which is labeled. I mean, each data item has its own unique class. You could see this label in this way. Of course, if I'm speaking about a classification problem, or more exactly, if the output of my system will be a class. There are also regression problems when the output of my system is a number. Okay, but anyway, I'm knowing in a first phase this association between the input and the output, and this enables us to perform the training of our models in a, once again, in a supervised manner. As Daniel pointed out earlier, this process is tedious, it's complicated to have labeled data set. Why? Because you have to have experts for that. And probably you would like to employ, in some cases, unsupervised learning. In this situation, obviously the supervisor lacks, and the system by itself should be aware about the structure of the data, and it should organize itself in order to finally create, as you could see here, some data clusters. So some associations according to some specific features found in those data. Okay. In between supervised and unsupervised learning, there is also semi-supervised learning. I guess it's not present. Oh, it's present here. Today, it represents a very appealing approach due to, once again, due to the lack of labeled data sets. And more exactly, I'm speaking about huge data sets. Okay, a pretty interesting form of learning is represented also by this reinforcement learning. It is sometimes called learning through interaction. And I'm all the time using this example when I'm presenting this concept to my students. I say that reinforcement learning is similar with training a dog. Why? Because it cannot understand you directly when you are saying, please, bring the stick back to me. Obviously, the dog does not understand this, the human language, but it will perform certain actions, and you have at your disposal a reward, let's say like this, if it behaves well, if it fulfills the goal, if it brings that stick, or otherwise you could punish some undesirable actions. So through this mechanism of rewards, negative and positive reward, the agent will learn inappropriate behavior or policy in a certain environment. So this is reinforcement learning. Why it is useful? Because sometimes the agents may discover strategies, ways of acting pretty different from human approaches. So it's a way of gaining knowledge autonomously. And yes, we already noted some use cases, very well-known use cases, like beating the world champion of Go. Go, it's pretty complex. It's not like chess. You cannot employ brute force like it was done years ago by IBM with Deep Blue, if I remember correctly. So due to the countless ramifications, branches in game, you cannot follow a strategy in which you which enables you to explore all the possibilities. It's pure and simple impossible. So you have truly you have to understand deeply and truly all the strategies, the rules, and everything associated with that particular problem. Okay, maybe this one is an example of super intelligence. Why? Because in this particular problem, an artificial system is way better than a human. Now, coming to deep learning. Deep learning goes tightly with the concept of neural network. So deep learning cannot exist without a deep neural network. So we have to refer to both terms, neural networks and learning in this context, or deep learning if my neural network it's a deep one. And of course, it is today one of the most successful machine learning approach. There are a number of reasons for that, and probably the most important thing which sparks this the interest into deep learning and which facilitate the appearance of this concept was the quantity of data, especially in applications like image processing, video processing, and so on. So using deep learning, we are able to process huge amounts of data, which are today available. Formally, we could define an artificial neural network like a signal processing system. But this signal processing system, it's definitely inspired by the biological neural networks, so the computing systems which reside inside our brains. And this is why they have a large number of elementary processors. Let's call them neurons or nodes. They are definitely cooperate toward a certain goal or to solve a specific task. And what we are having here is the most simplistic, but nevertheless still used model of an artificial neuron in comparison with a biological neuron. This model is called McCulloch-Pitts model. Once again, there are countless numbers of other artificial neuron models, some more sophisticated, more close to the real operation of a biological neuron. Let's mention here just a spiking neural model. So coming back to this simplistic but still used model, we should note that we have some inputs, a number of them, and an output, which corresponds to the notion of dendrites and axon, the output of the neuron. But more important than that, we are having these synaptic weights. Along with this bias from the neural model, enable us through training to get the knowledge, or to memorize, or to understand a specific problem. So here at the synaptic level, the information, or most of it, is stored there. Okay, now knowing how to create an artificial neuron, we could connect more of this type, and we will finally end with a neural network. Because today deep neural networks are of a real interest, I may stress the fact that a deep neural network differs mainly in the number of layers. So between a traditional, it is called shallow neural network, and the deep neural network, the only difference is the number of hidden layers, the layers between input and the output. What we are seeing right now, it's a so-called fully connected architecture, because each neuron it's connected with all the neurons from the previous layer. Moreover, it's a feed-forward architecture, because the information or the signals are passing from the input to the output exclusively. So there is no feedback in this situation. So I may say that this is probably the most simplistic deep neural network architecture we could find. Those neurons are of the type we have seen earlier, of McCulloch-Pitt type. Okay, now we refer to the architectural aspects. Now, how exactly it learns will be a next topic, but until that, let's refer briefly to some typical deep neural network architectures. Now, what I want to say is that these numerous models are suitable for different applications. For example, a convolutional neural network will probably be used in image processing applications, but a recurrent neural network may be more suitable to the kind of applications you have spoken earlier. Why? Because they are able to cope also with the temporal information holding in the input patterns. A convolutional neural network, or a feed-forward neural network like this one, does not have the capability to deal with the temporal relations between the input. Moreover, this unidimensional input is not suitable for image processing, so probably in this situation, the input will be at least two-dimensional. Okay. I don't want to get too much into details. From this diagram also some more modern architectures are missing. I'm thinking about transformers, which are in fact some recurrent neural networks. Even ChatGPT could be categorized as a recurrent neural network plus some generative component. In fact, GPT comes from generative pre-trained transformer. Okay, so once again, this is not a complete picture of all deep neural network architecture, but some of the most important types. Now, how exactly we could train them? I may say that most of them are employed a supervised approach. As I've said earlier, in this situation, we need a labeled data set, a data set with examples. And there are many possibilities to implement this supervised concept of learning. But one of the most common algorithm is the so-called error correction algorithm or concept. In this situation, we have to define the error, as you could see here, at the neuron level, output neuron level, as the difference between what I want to have as an output F and what I'm actually having at the output level. So once again, this difference is defined with respect, to this layer, to the output layer. So imagine that here I'm having a picture of a number, a digit from 0 up to 9. And I should have here 10 neurons for each class, one output. Of course, initially, due to the fact that these weights and biases are randomly chosen, I will definitely have important errors between what I want to have and what I'm actually having as an output. And I have to take into account all these errors by defining a so-called cost function. Daniel said something about loss. It's almost the same thing. The truth is that we could also add here not just errors, but some other terms which could take into account, let's say, the complexity of the network. And finally, what I have to do is to minimize this function, represented, for example, here, as a function, once again, of weight and biases. So at a certain moment, initially, I'm somewhere on this surface. But my goal is to obtain or to find the minimum of this function somewhere here with respect to weights and biases. Now, imagine that a deep neural network has at least tens layers, probably millions of such free parameters, which should be adjusted during the training. So this surface, it's a pretty complex one, and the problem is not very simple. This is why it takes so long to train a large neural network. Okay, now the most common way of founding this minimum is through gradient descendant principle or algorithm, and countless flavors of this concept. In fact, it's pretty simple. If my function is of just one variable, then this principle said that I have to modify the weights, including the biases, in the negative direction of the gradient of the cost function. Eta here, it's called learning rate. So I will modify in the next step Wn plus 1 towards the point of minimum. So these are the very basics concepts behind these structures called deep neural networks. Now, I would like to point out some thoughts, some recommendations regarding the implementation of this technology. First of all, you will have to choose an operating system, and I will definitely go with a Linux for that. Although Windows offers today what is called the Windows subsystem for Linux. So you could have the same capability today, some capabilities offered by Linux into Windows, but in the final instance, we are speaking about a Linux solution, which is probably the best for any application implementation. Why? Because we will see immediately we need some frameworks in order to implement a deep neural network. And those frameworks are currently offering support for sure for Linux. Some of them, one of the most important, which is TensorFlow, dropped the support from Windows from few years. So yes, from the operating point of view, we will need probably a long-term supported version for our implementation. Now, let's come to the framework level. Here we have, on one hand, some offline, let's call them like this, solutions installed on-prem, on a PC, in other words. And you could opt for a commercial solution. MATLAB, in this sense, offers through some specialized toolboxes very, very good support. More exactly, deep learning toolbox is of interest, and statistics and machine learning toolbox. I don't want to insist too much because I'm sure that all of you knows what I'm talking about. The disadvantage is mainly the price. It's pretty expensive. So for individuals, it's not recommended. And also my impression is that all the time MATLAB is well behind the state of the art in the field. So what is in 1 year hot in the domain, you will see probably next year implemented in MATLAB. So there is a pretty large delay between the things in this respect. So probably and preferably I will go to a open source solution with a high level language, probably Python. Basically Python is the de facto standard in artificial intelligence. So artificial intelligence goes pretty well with Python. The problem is you will need an entire ecosystem. Python by itself, it's not useful. You will have to use many libraries, frameworks, as I said earlier. Now, for that, you will need to encapsulate all these distinct libraries, and that will be done using some tools like Anaconda, Miniconda, Conda, Pip, in order to manage the packages and libraries which will be used in a project. The project could be executed, designed, debugged into some integrated development environment, and my recommendation goes to PyCharm, which is probably the most powerful tool for developing the application. It is costly also, but it has some educational licenses, or through to Visual Studio Code. It's much lightweight than PyCharm, and you could do basically the same thing. It's also free. Or especially for presentations and for teaching, you may employ the concept of a Jupyter notebook. It is cell-oriented. It's pretty similar with MATLAB in this respect. So you could, first of all, combine images, equations, and code and see the result of your code immediately. So one of these three solutions will be preferable, along with a framework, a deep neural or deep learning framework. Basically, each big name in data handling has its own tool for machine learning, deep learning applications. TensorFlow, it's my favorite, but it's a personal choice. It comes from Google and is more oriented toward industrial applications. So you will probably manage more easily to deploy such a model into production. On the other hand, PyTorch, coming from Facebook, it's more research oriented. It's probably preferred by researchers in academics. It's pretty Pythonistic in all the concepts. So they are offering almost the same features. Of course, as I said earlier, there are other tools coming from Amazon, for example, MXNet, or from Microsoft, or from IBM, but I will stick to one of these two possibilities. Now, because our computing platforms are not typically power enough to train such models, We have at our disposal also a so-called online paradigm for implementation. It's basically everything we have seen earlier, but in an online web-based interface in the form of this Google Collaboratory. They provide you free resources, I mean software, as well as hardware, to run such projects. Of course, there are some restrictions in the free version with respect to the time you could train a model. I'm not very well aware right now which are the limitations, but a few years ago were just 24 hours of continuously running an application. And you could benefit of a good hardware for running the code, like those TPUs. We will discuss immediately about the hardware. So this is an interesting alternative and an appealing one because it's free and it's powerful enough. Okay. There are also, let's say, optional tools you may want to employ in development, an AI project, a machine learning project. For example, a solution for code hosting, and also a solution which offers versioning control. I have to store somewhere safely my code, and also I will probably like to work collaboratively. I mean, many software engineers working at the same project. So for that, we may like to have a resource like GitHub. Moreover, GitHub, it represents a very good source of inspiration in machine learning projects. You will find probably every kind of application there. It is true that storing your code on GitHub will allow you to easily load it into Amazon, Google, and Microsoft platforms. Moreover, it has an interesting feature called Copilot, which is some chat GPT for code. But in my opinion, this is way better than ChatGPT for code generation. ChatGPT is more general tool, but Copilot it is designed for code generation. It's not very expensive. Few dollars per month, I guess. So you could describe what would you like to do in your code, and you will probably get the right implementation as an output of this Copilot. In large project, you will also like to pack all the things into a so-called container, including the operating systems and all the software. A lot of libraries, drivers must be present there in order to have a functional model. And probably if you want to monitor and to retrain, to deploy, to train on various platforms, you will like to employ also Kubernetes for that. But this is the case of more complicated and sophisticated projects. Now, from the hardware perspective, definitely a GPU will help in this endeavor. The problem is the availability of such processors, graphical processor unit. The fact that they are pretty expensive, and basically each year appear new models, new capabilities, and we may say that rapid obsolescence it's an issue in this field. Anyway, my option will go through an RTX graphic card, which is a balanced option in terms of expensive and performance. At least 12 gigabytes of RAM will be needed for a medium complexity application. On the other hand, you could think about the so-called edge AI concept, which is mainly used for the inference phase. I mean, you already trained your model, you have ended the design, and you want to include that model into a certain larger system. So it's a kind of embedded system. It has numerous advantages. Think about the cost, which is much lower, the power consumption, the latency, reliability, and also security. Why? Because you have your device near you. No, you don't have to use internet in order to store the data and to operate it. In this way, you are decreasing the latency. So some examples from this category. Probably this one is the one of the most performant solution in the field of edge AI. And what we are seeing right now, it's called Google Coral Edge TPU. TPU, it's a machine learning accelerator. It's better than a GPU in every term. It comes from tensor processing unit. And the concept of tensor is somehow related to those weights and biases we have seen earlier. So this is of the size of a credit card, and provides impressive performances. We use it in image processing, in real-time applications. I mean, applications which need, in this case, extremely high refresh rates. There are also other solutions, and I don't want to get too much into details. For example, some of them are coming from NVIDIA. Again, in this situation, we have no more than a GPU here, but a mobile GPU. Or even from this company called Imagination. They have a long tradition in machine learning accelerator. They are powering Apple cell phones with such kind of accelerator. Moreover, they provide very interesting teaching materials in this domain of edge AI for free. I know because we have made some reviews for them. Okay, lastly, the end-to-end full cloud solution will probably employ Microsoft, Amazon, or Google. All of them are providing specialized tools for machine learning implementation. And this time I'm saying that they provide both hardware and the necessary software through some virtual machines configurable architecture. So in 15 minutes, you will have a fully operating system for your experiment. The drawback of this approach is again the price. There are some free architectures, some free virtual machines, some credits for experiments, etc. But they are good for limited experiments, not for large-scale projects. Of course, for individuals, a company may afford to pay for such services, which are pretty nice once again, but pretty expensive. Okay, I will try to approach to the end of the presentation by saying that we are using such technologies mainly in 3 domains. And by we, I mean the Intelligent Embedded Vision Research Group. It's a small research group at the University Polytechnica from Timișoara. And we are developing applications in the automotive domain, mainly in prediction and perception areas. Prediction, we are concerned with the trajectories, future trajectories of traffic participants, like cars, bicycles, pedestrians, and so on. And perception, currently we are working with 3D data inputs, with LiDAR data, in order to segment, to classify, to detect objects from such kind of sensorial input. Here is also some fusion problem, because in a modern automobile, you will have also video cameras, radars, not just LiDARs. Healthcare, it's another topic. Here we are working with our colleagues from Medicine and Pharmacy University in order to elaborate some computer-aided diagnosis systems, mostly in the liver pathology. And we are proud to say that our solutions are probably better than a very experienced physician or doctor. And lastly, some biometrics applications. Currently, just ReID and gaze are among our preoccupation. Gaze, again, in the context of an automotive applications. Okay, thank you for your attention, and if you would like to formulate some questions, we have 5 minutes at our disposal, and also you could do it by email. Once again, I will like to stress the idea of Daniel. I cannot hear what is talking into the audience, so maybe.
Thank you, Catalin. Now
we will find another possibility.
Catalin,
yeah, right now I'm hearing you.
Yes, the microphone was turned off. Sorry, during your presentation, our microphone. So that's why you didn't hear anything from our side.
All right.
So now we are open to questions, discussions, if there are any. Seems that nobody has any question. Many thanks for the presentation, and being one of our collaborators as university, so we have a close collaboration with Timișoara, not with your group, but with the group in electrical engineering faculty. We can extend it. So we will keep in touch somehow, and maybe we'll start working somehow together also in this area. You can help us for sure.